Today we're going to explore group 15, pnicogens. So that is where you have nitrogen, you have phosphorus, you have arsenic and antimony, and you have bismuth. These are the pnicogens. Group 15. So what is special about them? We have 2 nonmetals, 2 metalloids, and 1 metal. When in an ionic bond, nitrogen, phosphorus, and a lot of these rest will have an oxidation state of a +3 charge. However, when they're in non-metal covalent bonding, that gets interesting because these two, instead of just having a -3 charge, they can also range to having a +5 charge when in certain compounds. As you approach down the group, the oxidation state that is negative will become less stable. So what that really means is your oxidation state is more likely to increase to be more positive because it's more stable. So bismuth will typically have a +3 oxidation state that makes it the most stable, while antimony and arsenic will depend. So antimony and arsenic here, they actually have a whole bunch of possible oxidation numbers. So it can go from -3 to +3, and this one is also -3 to +3. So I just say take it with a grain of salt. But what tends to happen is when something reacts with excess, such as excess oxygen or excess fluorine, they will tend to want to retreat to a more positive oxidation state. So that means if you got a phosphorus reacting with excess oxygen, phosphorus will likely adopt a high oxidation state. Whereas if you have a reaction where you have limited reactants, such as limited oxygen, your elements here will tend to enter into a more negative oxidation state. So when you do problems that ask you what is going to be the product of these two reactions, and you have excess or limited reactants, that's how it would affect the oxidation state, or aka the charge on these atoms in covalent bonds. So this is only for covalent bonds. For ionic bonds, it's way simpler. It's just a pattern that most of them will be a -3 charge, but it's usually the nonmetals that need this kind of framework here. Okay, now let's talk a little bit about nitrogen. So nitrogen can be extracted through fractional distillation of liquid air. So that is when you separate oxygen from nitrogen from air. So fractional distillation of liquid air. And because you're separating air, that's also the same way that you get oxygen, fractional distillation of liquid air. Now, the N2 bond is really unreactive also because of its triple bond. So it's very unreactive. So it's good for blanketing gas. Also, just a fun question here. So phosphorus 3, which one is more unreactive? Well, actually, nitrogen 2 is much more likely to be unreactive than phosphorus 3, because according to the theory, if you want a good pi bond, triple bonds are made up of 2 pi bonds and 1 sigma bond. If you want a good pi bond to happen, which means a strong pi bond, the property that they want is such that it has to be on a smaller atom. Phosphorus is way too big compared to nitrogen, small atom, so that electrons on 2p orbitals are closer together so that they can have this triple bond to be stable. So proximity is very important for triple bonds to be stable. So that is why nitrogen, the diatomic atom, is very, very stable. Okay, so nitrogen can also be used as a cryogen. A cryogen is a low temperature refrigerant, but this is nitrogen too that can be a cryogen. Helium is a monoatomic gas that can also be a cryogen. Okay, that's all for nitrogen now. Phosphorus is a very interesting element. Phosphorus has a lot of allotropes. So that means a different form of one element. So there is a white phosphorus and there is a red phosphorus. So white is very, very toxic. Very, very toxic. And it has a low melting point. So what you need to know is that the white phosphorus is very reactive, very toxic reactive, because of its bond structure is strained. So it does not follow your good old Lewis diagram where ideal bond angles or non-ideal bond angles are just nicely sitting there, but it's very strained, which means it's very reactive. So then we have to store it in water. Cannot store it in open air. Must store in water. Okay, whereas for red phosphorus is just P solid. White phosphorus is P4. Red phosphorus is non-toxic. It has a high melting point. It's unstrained and it's in a polymeric chain, which means it is altogether less reactive. So fun fact about red phosphorus, when you strike a mattress surface, it's actually red phosphorus being quickly transformed into a small amount of white phosphorus.